70% of the world's surface is water, and this ocean is vital for our survival. In fact, 50% of our oxygen comes from the ocean. It directly feeds over 1/3 of the world's population, and in economic terms, the ocean is the 7th largest economy in the world. Yet, we have only explored about 5% of this vast body of water. However, this is about to change, and we aim to play a part in making it happen. In 2017, the Swedish Maritime Robotics Center, SMARC, set out to develop the next generation of maritime robotics. By doing so, SMARC would be able to contribute to global societal benefits in 3 important areas: ocean production, safeguarding society, and environmental monitoring. For each of these areas, SMARC generated a number of scenarios highlighting key research challenges such as remote operations in polar regions, protection of coastal areas and harbors, infrastructure monitoring such as algae farm operations, or tracking and finding substances in the water volume. To succeed, the project needed to show that autonomous underwater vehicles were able to operate in very challenging environments for longer periods and with less need for human intervention than was considered possible before. Several of these capabilities have since been demonstrated during a demo period at the island of Askö and through expeditions to Antarctica. The SMARC project has now reached its midpoint, and it's time to have a look at what some of the research teams involved in the project have achieved so far.
So the mission planning and execution framework of an AUV needs to be robust, transparent, and modular. Robust, since these vehicles are going to work very far from human helping hands. Transparent, so that non-expert user can understand and predict what the vehicle are going to do in different situations. And modular, so they can enable and disable particular behavior components depending on the mission. And in our research group within SMARC, we have developed a technology that meets these 3 requirements. And that is based on a technology called behavior trees.
My name is Nils Bore, and I'm a postdoc at KTH in the area of computer vision and robotics. I research applying machine learning to different kinds of sonar data in order for the AUVs to understand what they're actually looking at the seafloor. It's exciting because the subsea environment is such an unexplored area of our planet. And the research that we're doing into these sonar sensors allow us to extract much more information about this environment than has been possible before. KTH is at the forefront of applying machine learning to sonar data. What we're doing right now might help kickstart this revolution that will eventually come of machine learning in the underwater environment. We use similar techniques as in autonomous cars, for example, to estimate the seafloor geometry. One of our success stories is how it allowed our students to easily start working with underwater data. It has really piqued their interest and resulted in several academic papers.
I work on a specific area called SLAM, Simultaneous Localization and Mapping, in which a mobile platform needs to be able to create a map of its surroundings as it navigates and use that map to stay localized with respect to it. This is a chicken and egg problem in which you need a map to know where you are, and you need to know where you are in order to create a map. This makes the problem of autonomous localization and mapping way more interesting, but also way harder. What's exciting about SLAM for robotics is that it combines a strong theoretical background on the SLAM as a math problem. You also get the chance to implement your solutions on an actual platform, on a mobile robot, and be able to see that what you come up with actually works. The big purpose is that our robot doesn't get lost. We need to be able to know what it is and the environment around it, just so that they can find a way to finish the mission and come back home. At ASCO, we have successfully tested for the first time that our very compact AUV is able to stay localized in open waters with enough accuracy to find and geolocalize a sunk car.
So far, we have presented our progress towards achieving robust and transparent mission planning and autonomy, perception, meaning our eyes and ears underwater, as well as precise navigation and localization to know where we are. An additional scenario could be to look for a substance in the water column, like a sniffer dog trying to pick up a scent.
Currently, we are testing our Raman spectrometer to find the lowest detection limits for some polyaromatic hydrocarbons, and we assimilate a lot of spectra for building a machine learning algorithm that can detect the PAHs in no time from all the backgrounds and noises. A lot of challenges await us, from time for testing, finding low detection limits, playing around with different components of the instrument, and transforming everything into an underwater sniffer.
In my research, I'm pushing the boundaries of making underwater robots more efficient and agile. Therefore, I'm working on controllers and simulation models to simulate aggressive maneuvers with underwater robots. With these kind of maneuvers, we can create new capabilities and use cases, and we can have new mission scenarios in the real world. As an example of one such mission, this summer we combined research in autonomy, perception, and localization in order to autonomously find a submerged Mini Cooper in the island of Askö near Stockholm. The AUV searches for the submerged Mini Cooper by following a mission plan. In order to follow this mission plan, an autonomy package called a behavior tree sends commands to controllers, which in turn find the way using localization modules which are already developed. Throughout this whole process, the AUV searches through an area and it finds the car using the cameras on board. Once the car is found, it can also replan and maybe inspect the car, or if there's an emergency, it can take emergency actions like coming up to the surface. The mission that we tried was a great success, and we were able to demonstrate autonomy.
Robust underwater communication over a long distance is one of the more difficult things to accomplish, where environmental factors plays a huge role in the quality of the link between AUV and AUV operator, but also AUVs in between each other. Therefore, on Lolo, we developed this payload deployment system where we can at any time deploy one or multiple acoustic nodes, which essentially works as routers in our underwater network, and potentially increase the robustness and also the distance from which we can communicate. This feature can be crucial for missions where we can't surface the vehicle, for instance in remote reconnaissance missions or under ice missions.
In harbor protection areas, a key capability is to find known targets, which was demonstrated at Askö with the Mini Cooper. In order to extend the capability for operations in unknown environments, we have also demonstrated the capability of dropping sensor nodes to, for example, create an ad hoc communications network. In addition to the Askö demonstrations, we have also participated in Antarctic expeditions, sending underwater robots below glacier tongues.
We were the first humans to measure below the Antarctic glacier Thwaites, argued to be one of the keys to future sea level rise. Thanks to the project SMARC, we were able to send an AUV, the University of Gothenburg-Rahn, below the ice and gather unique data for ocean depth, ice thickness, water temperature, and the heat flux moving from the ocean to the ice. This data will seed new and improved models for sea level rise, one of the greatest challenges humanity presently faces.
Now that we've told you about some of the things we have achieved so far, it's time to have a look into the future.
Well, by definition, SMARC is a project. We are approaching the midterm review. We hope to pass that with flying colors, and then it's only a few years left. We need to start thinking about what comes after SMARC. I think SMARC could be the foundation for the Swedish Underwater Technology Center.
In the years to come, within SMARC, we will continue to focus our research on achieving key capabilities for our benefit areas. And we will set demanding goals for demonstrating these capabilities in very demanding environments. We will also extend SMARC to tight collaboration with Sweden's largest research program on autonomous systems, the Wallenberg Autonomous System Program, WASP, by performing joint demonstrations with a multitude of robotic systems.
What I dream of is to connect the different things that I see here. Communication underwater onto the surface and have flying things in the air. Do some bigger task on system level together and hopefully share some data and try to do something that connects it together.
Over the last 3 years, SMARC has brought together key industrial and academic stakeholders in an internationally unique collaborative environment, firmly establishing maritime robotics and underwater technology research in Sweden. The project is set to conclude in 2024, and during the upcoming second half of the project period, SMARC will focus on integration of software and hardware and continue testing its maritime robots in the very toughest of real-world environments. As we've seen, the project is running according to plan, and the goal is clear: to achieve a transformational shift towards a truly disruptive technology and then transfer this technology to industrial partners in order to provide the largest societal benefits. The best is yet to come, and you can follow the project's progress at smarc.se.